Hey everyone, welcome back. Today we're going to have an algebra problem, or more precisely, a fairly easy ring theory problem that is written on the board, which says factor x to the 8th power minus 1 over z2, z3, and z5. And of course, when we say trying to factor out a polynomial, we usually would like to factor out completely, or in other words, we would like to factor out into the product of all the irreducible polynomials over the rings that we have. So, in fact, we have z2, z3, and z5, which are not only rings but also known as field in abstract algebra. But what does it really mean? It only means that for the coefficients of the polynomial we have, the coefficients will be elements of the given rings or given fields, such as z2 will be containing the elements that are integer remainder after dividing by 2, which means either have coefficients 0 or 1, and then z5 will have coefficients of 0, 1, 2, 3, and 4, like that. So before we move on to the solutions, you can pause the video and try yourself first. Okay, so let's see what we can do. So there are a couple ways of doing this kind of problem, but the fastest way that I personally think would be first, just consider of the given polynomial and factor out over the integer rings, or you can just consider as just regular factorization. Then we will try to see what we can reduce after we factor out completely based on the rings that we're looking for. So for the given for a given polynomial x to the 8th power minus 1, we can use the difference of we can use the difference of squares formula to give us x to the 4th power minus 1 times x to the 4th power plus 1. And for the first term, x to the 4th power, again, is also a square, so we can just use it one more time. And if we continue doing it, we'll end up with the following: x to the first power, or just x, minus 1 times the quantity x plus 1 times the quantity x squared plus 1 times x to the 4th power plus 1, which is already found at the beginning. Good. So now let's see. We have 3 different fields. So let's start off with the first one. The first one says we're going to factor out over z2, which means the coefficients will only be 0 or 1. In other words, if we see something that is 2 or more, or if we see something negative, we can just try to divide by 2 and then find the remainder part. In other words, if we see plus 1, of course, 1 divided by 2 is 0, remainder 1. But if we see minus 1, in fact, we know that minus 1 can be written as negative 1 times 2 plus 1. Meaning, if we're trying to think it as an element in z2, negative 1 will be the same as positive 1, or you can say equivalent to in mod 2. Therefore, in our case, we can replace all the plus 1 into minus 1, or we can do it the other way around. So this gives us x to the 8th power minus 1 equals x minus 1 times x. Here we're going to replace the plus 1 by minus 1 based on the results that we found. So similarly, we have x squared minus 1 times x to the 4th power minus 1. Great. So now we can actually combine the x minus 1 and x minus 1 together to give us x minus 1 squared. And next we have x squared minus 1, which is something that we have already done, and we know the results will be x minus 1 times x plus 1. But again, x plus 1 is equivalent to x minus 1, so we will just end up with another 2 copies of x minus 1. Last but not least, we have x to the 4th power minus 1, which can again be factored out into this part here. And again, this can be reduced into x minus 1 to the 4th power. Therefore, we can just combine all of them together and say x to the 8th power minus 1 is equal to x minus 1 quantity to the 8th power over the field Z2. Good, so we already finished the first one. Now let's move on to the second one. Okay, so for the second one, we have the field Z3, which contains 3 elements, 0, 1, and 2. So of course, we will just start doing from what we ended up with, which is x to the 8th power minus 1 is equal to the right hand side. But this time, since we have 3 different elements instead of just 2, we also need to know the relationship between other integer that's outside of the other integers that are actually not elements of the given ring. So for example, here we have 0, we have 1 and 2 as the element of the ring, but minus 1 or negative 1 is not part of the is not equal to any of these elements. So how are we going to convert negative 1 to part of the ring? Here is what we're going to do. By the definition of Z3 is saying that is the remainder, integer remainder, is a. So by definition, Z3 is a field, or you can consider it as a set of elements, so that these elements are the remainders after an integer is divided by 3. Therefore, when we have some numbers or some integers that are actually not 0, 1, and 2, we're just going to take the division and find out what the remainder is. For instance, we have negative 1 here, which is equivalent to negative 1 times 3. And again, that is the other way of thinking of dividing by 3. And this is going to end up with plus 2, which means the 2 here will be the remainder of negative 1 as we divide by 3. Or in other words, we can say negative 1 is equivalent to 2. So how does that help? Because we can also try to imply this idea for other numbers, such as 1, we can write it as 0 times 3 plus 1, of course. But we can also write it as 1 times 3 minus 2. In other words, we can rewrite 1 as negative 2 here, even though negative 2 is not part of the element that we have. So why are we allowed to do that? Because we're saying that those are in the same equivalence class. Or in other words, they actually have the same meaning, even though they have different representations. So the reason that we would like to rewrite 1 as negative 2 is because, again, it will be easier for us to try to factor out something if we have something positive minus some other terms, especially if we consider of the difference of square formula that we have learned in high school. So this is what we will have. The first term will still remain the same. We still have x minus 1. The second term will turn into x minus 2, as we claim that positive 1 is equivalent to negative 2. Then for the next one, we will have x squared minus 2. Last but not least, we will have x to the 4th power minus 2. Great. So now we see that the first two factors are already in the linear term, meaning that they are irreducible, or in other words, other than just the elements of the ring that we have, or the units, we have nothing else that we can factor out from it or degenerate into two smaller degree factors. So the first two terms are already determined. Next, we have x squared minus 2. So suppose that it is factorable, meaning that we can break it into two smaller terms to multiply it. Suppose that it is factorable, meaning if we are assuming that it can be reduced into two small terms with a degree that is less than this, then in this case, we will assume that there exists some a value and some b value such that the product of x minus a times x minus b is going to be equal to x squared minus 2 over the ring that we have, which has 0, 1, and 2 as our coefficients. In other words, we will assume that a and b will be some elements 0, 1, or 2. But if we just multiply back in, we will find out that there's no such element a and b exists, so that the product will actually end up with x squared minus 2. Therefore, we will say that x squared minus 2 is irreducible, meaning that this is already the lowest term that we can actually get, and it cannot be factored out into two smaller terms. Great. Last, we need to check x to the 4th power minus 2. And for this one, it will be a little bit tricky because we can actually break it in two ways by the definition of factorable. So suppose to the contrary that x to the 4th power minus 2 is factorable over z3, which contains 0, 1, and 2. Then we have two cases. Case 1, there exists some linear term or linear factor, and then we will of course end up with something like this, such that the product of these two will be end up with x to the 4th power minus 2. But if there exists a linear term, we can just use the factor theorem, which says, suppose it's factorable into some linear term times some other polynomial, then we can then for the linear term x minus a will be also considered as a solution of the original polynomial. In other words, if we replace x by a, the original polynomial will end up with 0, with no remainder. Now, the question is, does such a exist? Let's see. Suppose x equals 0. Then the given polynomial, x to the 4th power minus 2, is of course equal to 0 minus 2, which is negative 2, or which is equivalent to 1, but definitely not 0. So x equals 0 is not a solution. In other words, x is definitely not a factor of x to the 4th power minus 2 in our case. Similarly, if we substitute x equals 1, we will get 1 minus, we'll get 1 to the 4th power minus 2, which is equal to negative 1, or in other words, is equivalent to positive 2, but again, it's not equal to 0. So x minus 1 is also not a factor. Last, if we replace x by 2, we get 2 to the 4th power minus 2, which is 14, or equivalently 2, but again, that is not equal to 0. So x minus 2 is also not a factor of x to the 4th power minus 2. Therefore, our assumption of there exists a linear term factor for x to the 4th power minus 2 is not valid. So now we need to move on to case 2, which is to set up as a product of two quadratic factors. In other words, we will assume that both are degree 2 polynomials. And then we just need to multiply in and try to find out the conditions that will satisfy. But again, if you just follow the steps, I'll leave it to you guys to check it. But if you follow the steps, you'll find out that no solutions will exist. Therefore, our assumption that x to the 4th power minus 2 is factorable is incorrect. So, as a conclusion, x to the 4th power minus 2 is irreducible. Therefore, this will be our solution. Excellent. So now we can move on to our last ring, Z5. Okay, so now we're at the final ring, which is Z5. And again, Z5 means the remainders after dividing by 5. So the possible coefficients will be 0, 1, 2, 3, and 4. And again, we just need to follow what we did, similar to the last two examples. Then after we factor out, we just need to convert +1 or some of the coefficients into some other coefficients that are easy to help us factoring. So in this case, we'll rewrite, of course, the first one as it is. Then for the plus sign, we'll just change it to negative. And in this case, +1 will be the same as -4. And again, that is because 1 is equal to 1 times 5 minus 4. So it means -4 will have the same remainder as +1. So -4 will be equivalent to 1 in our situation. Then for the second factor, we will end up with x minus 4. And then the third factor will be x squared minus 4. Last but not least, we will have x to the 4th power minus 4. And again, this is the reason why it will be easier if we try to factor out, or we will try to factor out and also rewrite the coefficients into negative for especially the constant term. Because now we see that first two terms, of course, are irreducible as they are already linear. But the third term, x squared minus 4, is now factorable, and we can rewrite it as x minus 2 times x plus 2. And again, that is because x squared is a square, 4 is also a square. We can use the difference of squares to help us factor out. Last, we have x to the 4th power minus 4, and x to the 4th power is same as x squared squared. So using the formula, we have x squared minus 2 times x squared plus 2. Excellent. So now let's move around the steps. We have x minus 1. And then here we have x minus 2 term. Good. And then here it says x plus 2, but again, 2 will be equivalent to -3. And again, we can just think it this way. 2 is equal to 1 times 5 minus 3. Therefore, -3 or -3 will have the same remainder as 2. So -3 is equivalent to 2. And they're interchangeable. So we will end up with x. Instead of plus 2, we will write as -3. And then also we have x minus 4. Good. So now, here comes the question. Can we factor out x squared minus 2 or x squared plus 2? Again, when we say factorable, it means that it can be reduced into a product of two polynomials that has a degree smaller than it. In other words, if these two terms are factorable, each factor must be a linear term. So it will end up with x minus a times x minus b, similar to the other polynomial. But again, if one of the factors is linear, we know that we can use the factor theorem to help us to check whether it's true or not. So to find out, we just need to substitute the possible solutions into each quadratic term and see if the remainder is ending up with 0. So first, we're going to look at the x squared minus 2 term. We see that when x equals 0, we don't get the whole thing equals 0. And if we check all of them, none of them will actually give us 0. So it means that no matter what we choose here, none of the values will give us the quadratic term equal to 0. So the assumption of having a linear factor is incorrect. And since there's no linear factor for this quadratic term, it's not possible to actually factor out x squared minus 2. Therefore, x squared minus 2 is already irreducible. Similarly, if we try to substitute all these possible answers into the term x squared plus 2, we will not end up with the remainder equal to 0. Therefore, we can now conclude that x squared plus 2 is also irreducible. And that gives us the answer of x to the 8th power minus 1 over z5. That's it. Thank you for watching. I'll see you guys in the next video.